I'm Marcus from BitCraze, and I will be talking about Crazyflie and positioning. So positioning is a really important part of the Crazyflie ecosystem. But a lot of the times we get questions, what system should I use? What are the pros and cons of these systems? And so on. So this workshop will be focused on giving an introduction to different technologies and different positioning systems. We're going to talk a little bit about how they're used with the Crazyflie and some of the pros and cons with the different systems. And at the end, we're also going to be seeing a video of some flying and be talking about how you can mix the systems together. So first of all, why would you like positioning? Well, one of the reasons is that the Crazyflie is unstable. It has an IMU. You can read out orientation of a platform, but even if you tell it to stay really, really flat in the air, it's still going to drift to the sides. So that's one problem. Another problem is if you want to swarm. So you want to fly a bunch of individuals around. You want a common knowledge of coordinate systems. You want to know where everyone else is going, and so on. Autonomy is another reason. You might want to fly the platform around by itself, and then knowing where you are is a pretty important thing to do. And another example is ground truth. So like we've heard from, if you listen to Klaus and his team before, they used positioning systems for ground truth for their algorithms. So if you want to evaluate how good your algorithm is flying with something else, like for instance, trying to minimize the drift of IMU, then having a way to measure this is really important. There's a bunch of other reasons. This is just a few examples. So the question is how. So there's a few concepts. First of all, there's relative versus absolute positioning. So relative positioning is when you start up and you tell the platform to go 1 meter forward, 1 meter backwards. You start at 0 and you have no concept of where you are, just how you're moving. The other one is absolute positioning, where you have coordinates. So you know I am here, I can go there, I can go there, I can come back to the same point again. Another concept is off-board versus on-board positioning and post estimation. So off-board is typically when you have a system that's looking at the Crazyflie, for instance, and the system will tell the Crazyflie, you're here. You can also estimate the pose, like this is the orientation you have, but you get the full solution sent to the Crazyflie. The other option is to do it onboard. So you will get some information from outside, and onboard you'll fuse this information together with the other sensors, IMU, and what other sensors might be available, and you'll get a position estimate or a post estimate. So we're going to be talking a little bit about these concepts, and we're going to be talking about the systems we have and how we implement this. So in its basic configuration, the Crazyflie doesn't have any hardware to support positioning, but we have a number of decks that you can add on top of the Crazyflie that will give it positioning capabilities in different coordinate systems, different positioning systems. Now, I would like to say the choice of positioning system depends a lot about what you want, what your use case is, what limitations you have, what you want to get out of it. So what I'm trying to present is some of the pros and cons, and then hopefully it's easier to decide what to use. So first of all, we're going to be talking about off-board absolute positioning. So this is when, like I said before, this is when an external system will tell you your position and or pose. A typical example of this is motion capture, but you could also imagine doing this with a webcam. We've used webcams, we've used Kinects, you can use the RealSense from Intel, for instance. So this system will be connected to a computer. The computer will figure out where the Crazyflie is or the Crazyflies, and it will transfer this information to the Crazyflie, and it will act on this. So with this kind of solution, there's a few pros and cons. One of the pros is definitely that you will know the position of all the individuals. So let's say you want to do something like you're flying a swarm and you want one individual to just fly through all the other ones. Now you know where everyone is, so you can tell the other individuals to part and you can fly through. Another nice thing with this is that, like I said, you can use different systems like a webcam Connect, and you just send the position to the Crazyflie and the pose. Some cons with this kind of setup is that it does give higher latency. So you have an external system that's trying to figure out the position. You have USB to Crazy Radio, you have Crazy Radio to Crazyflie, and so on. It also doesn't offer any onboard autonomy. So if you want to fly the Crazyflie by itself, or you want the Crazyflie to be able to fly by itself, this won't be possible without being connected to a computer with a Crazy Radio. So let's look at one of these systems. So one of the systems, like I said, is motion capture. So this motion capture offers absolute positioning or board pose estimation, and it works like you have multiple cameras around the room. The cameras will flash IR light, and you have markers on the Crazyflie that will reflect the light, and the camera will pick it up. The camera system and the software will calculate the position and pose, and this will be relayed. So like I said, you need markers. So there's a few different ways to do this. One of the ways is to use passive markers. So this is what we have on the picture here. So they're spherical, they're spheres that reflect the light. And in order to be able to identify each Crazyflie, you need to put them in different configurations. So maybe one configuration will be a plus, one will be a T, and the motion capture system will be able to identify each individual. And this might be troublesome if you have a lot of different individuals. There's a lot of different configurations, and you want to put the spheres as far away from each other and so as possible to make the identification better. Yeah, so one way to solve this, we have an active marker deck that's developed for Qualisys. Qualisys is a motion capture vendor and developer. So the active marker deck you can put on the Crazyflie, and it has some LEDs that will be identified by the system. And using the 4 LEDs, you can create a lot of different identifications, and the system will be able to understand which individual is which. And we have some we have some Qualisys support in our examples. Another good way is to use Crazy Swarm, a library for flying Crazyflies in swarms, and it supports single marker identification. So with this system, you only need one marker, and the system will take care of what Crazyflie is which. And this is also has some support for the active marker deck as well. So you can light up one LED, and it will be able to track it. Yeah, so we have in our lab we have a 6-camera system from Qualisys. It's about 7 by 6 by 3 meters that we use for flying and for ground truth. So some of the pros and cons of a system like this. The pros are that they have crazy high accuracy. I still remember when we got our Qualisys system, we put one of the spheres on the floor, a wooden floor, and as we were walking around the floor, we could see the floorboards bending quite nicely in the software. It has really good scalability. You can add more cameras. We've been in systems with 60 cameras. And it's also, if you want to use it as ground truth, it's some kind of de facto standard for ground truth for robots. Some of the cons is that the price is quite high for this kind of system. And also that it can be a bit complex, the installation and the usage of it. Yeah, so the next thing we're going to look at is, like I said in the beginning, the onboard absolute positioning. So in this example, you have a Crazyflie not being connected to a computer. So there's no external system that's feeding you the position or the pose. What we're doing instead is getting parts of information from the environment that we fuse together with the onboard sensors in the EKF to get a good position and a pose. So some of the pros of this kind of solution is that it supports onboard autonomy. The Crazyflie can fly around by itself without being connected to a computer. The latency is lower. You don't need to go through a computer, and you don't need to go through a radio, and you can also act on partial updates. So maybe you don't have the full solution, but you get one message from an LPS node, for instance, and you can act on this. One of the cons with this kind of system is then that you don't have a central knowledge of all positions. So if you want to control the full swarm together, cooperating in some way, you have to solve this in some way, since they're not connected together in a computer. One of the systems that support this is the Loco positioning system. Absolute position onboard position estimation. So there's no pose estimation with LPS. It's based on ultra wideband, so it's radio instead of the others that are optical. And there is a range of different algorithms that can be used. For example, two-way ranging, two-way 2 and 3. Which one you want to use might depend on your use case. Yeah, and we have this kind of system in our lab, of course. We have an 8 anchor system that's 7 by 6 by 3 meters, but we normally fly in TDI free mode. So some of the pros and cons of this is the pro is that it has a larger tracking volume. So you can have larger systems, and for example, the Lighthouse. There is some kind of graceful degradation. So using the Lighthouse, for instance, or a mocap, either you see the robot and you can track it, or you can't. With using the LPS, you can degrade it, saying that you only track in XY, for instance, or you could space out the anchors more, and the noise will be higher, but you'll still get some position. It also has other attributes like the non-line of sight. This is a lot depending on the material. So the LPS works with sending timestamps as radio messages to the Crazyflie. So you will measure the time it takes for the radio package to go through from the node to the Crazyflie. So if you have something in the way that slows down the travel of the radio, this will be affected, and the time will be affected, and the Crazyflie will think that it's further away. Something that has a lot of water in it, like a human, will affect the measurement more than something that has less water, like cardboard, for instance. Another pro is that it's not sensitive to sunlight. So some of the cons with this kind of system is that with the LPS today, you need to set up manually the system geometry, which means when you place the anchors around your room, you need to measure out the distance to each anchor. Also, the scaling could be better. We have used TDOI3, managed to scale it a little bit, but there's more work to be done on the software side. And then at the end, I put both pros and cons. There is a lot more noise. So the LPS is a lot noisier than mocap, for instance, a lot. But this could also be a pro if you're, for instance, interested in GPS emulation. This will look more like GPS. So another example is the Lighthouse. So it's also absolute position, onboard positioning, and yaw estimation. The Lighthouse uses, instead of a camera, it sweeps lasers across the room. So it will sweep laser beams that the deck that is placed on the Crazyflie will pick up. And as you get the different sweeps, you will be able to calculate your position. If you're interested in this, there's going to be an extensive talk this afternoon about this. It's based on Steam VR base stations. So Steam VR base stations are used for virtual reality gaming. The base stations are available off the shelf to buy. We've tried to, this is a positioning system that we use a lot. So we support both the Lighthouse 1 and 2. We use a lot Lighthouse 2 in our lab when we're flying. And we also have a paper together with Wolfgang Höning with lighthouse positioning, trying to quantify the performance of a lighthouse. And the setup we have in our lab is 4 by 4 by 3 meters with 2 base stations. So some of the pros and cons of a lighthouse then. Well, the setup is quick and easy, and the system geometry is automatic. So this is our positioning system that we use when we go to fairs. For the fairs, we use 2 tripods. We set it up. You put in one Crazyflie. The system geometry is calculated, and then you share the system geometry with the other individuals, and then you can fly in a swarm. So it has really good mobility. Another pro of this is that it is great value. The tracking, the accuracy of the tracking is really good. As always, there's more work to be done. But for the cost of this, the tracking is really good. Some of the cons of this kind of system, of a Lighthouse, is that currently it doesn't scale very well. So like I said, we support 2 base stations. Steam VR has support for up to 16 base stations, I think, and it's nothing that we support today, but we could. After listening to Klaus and his team talk, I also added that it's very sensitive to reflections, which we've also seen. So as the laser beams sweep across the room, if the laser beams are reflected in something like glass, mirror, Christmas decorations we had for the Christmas video, this will cause instabilities. And there's also, as always, more work we can do on the performance. So moving on to the last one. So onboard relative positioning. So this would be, like I said before, you don't have an absolute position and you don't have a position you can share with other individuals. But when you start up, you can move relative your current position. And the setup is very quick. There's no external systems. The cost is lower because there's no external systems. Some of the cons of this kind of tracking is that it will drift over time. So if you say go forward 1 meter, come back 1 meter, in reality, you might be going forward 0.9 and coming back 1.1. And there's no way to correct for this. Another con is that there's no common knowledge about the coordinate system, so you can't swarm the individuals together. So you will start up and you will be at 0, but you don't know where the others are. And even if they tell you I'm at 0, this means nothing to you. So our implementation of this is when the Flow V2. It uses optical flow, relative positioning, onboard position estimate. So what you will get out here is that you will know, as you're moving around, you will be able to see the floor. You can see that you're moving forward, backwards, and how far. And it will also measure the distance to the floor. And this is implemented using a ASIC for optical flow. It's actually the same kind of sensor that is in computer mice. The only difference is that this one has a lens, so you can see the floor in focus. Another possible implementation of this would be the AI deck, where we have a camera, we have the gap 8, where it would be possible to look at the environment and do optical flow using that. So some of the pros and cons with this kind of solution. Well, one of the pros is definitely quick start. You put on the deck, you put it on the floor, you start your script, and you're ready to go. Like I said before, lower cost also, and it has no external infrastructure that's needed. The cons, of course, it will drift over time. You have no swarming support, and performance is heavily dependent on the environment. So this deck, for instance, won't work when it's dark in the room. And to be able to track using the flow, you also want to be able to see a surface that has good features that you can track. So flying on a completely white floor with no features won't work very well. So after talking about all the different systems, we made a short video to show you the noise. So the idea is that using the different positioning systems, we're flying in front of the camera and trying to stand still for 10 seconds. And this is one of the tests. I think we want to try more stuff like flying around, showing this, but unfortunately we ran out of time on this one. So let's see. Yes. So here we have a comparison of 4 different positioning technologies, systems. So we have on the top left, we have a Qualisys aftermarket deck using the Qualisys mocap system that we have in the lab. The top right, we have the Lighthouse V2. On the bottom left, we have local positioning using TDOA3. And on the bottom right, we have Flow V2 with some patterns that we put on the floor. So let's see if it's working. So as you can see, like the motion capture system is rock solid. The Lighthouse, little less so. TDOA, not so solid. The flow stands still pretty well. I think the video doesn't really give local positioning doesn't do it justice, because it's meant to be used in larger areas where this kind of noise is probably not a problem. So the last thing I'm going to be talking about is combining these. So there are some pros and some cons with each of the systems. They have different costs, they have different properties. And one of the nice things with the Crazyflie is that we can combine them. So since we haven't been going to a lot of fairs because of Corona, and a lot of the time when we do demos, we learn a lot about our system and we challenge ourselves to use it. So we decided to do a positioning demo that we named the Hyper Demo. And the goal was to use the strengths of the different positioning systems to fly around through our office. So I think you can see the mouse pointer. Yes. So this is a meeting room, the room I'm in, where we have then put Lighthouse base stations, 2 of them. This is a path we're going to fly through the office, or we did fly through the office. So exiting the meeting room, there is no absolute positioning system coverage. So here we're flying on the flow deck, going around the bend, and then there's a long straight corridor. Initially, we wanted to do this long straight with a flow deck. Fortunately, it drifts a bit too much to the side, so we were hitting the walls. So to counter this, we put in some LPS nodes, and to only do tracking in XY, and then we use the VL sensor to do the SED. Flying along the corridor, we reach the end where there's a quite sharp turn. Here we put a lighthouse to have good positioning. And then we enter our flight arena, where we have both LPS and lighthouse base stations. So because of the fact that the lighthouse base stations has a lower standard deviation, this will be taken more into account and basically will be used when we land the Crazyflie. The demo was made using onboard autonomy. So the only thing we're doing when we're starting up is to tell each of the Crazyflies and the Bolt to go. Now it's your turn, now it's your turn. And then the actual flight path is done with a high-level commander, fully autonomously, and then it lands at the end. So a setup like this is definitely possible, but it does require some hacking. So like I said before, we only have support for 2 base stations. This system uses 5, which required some changing. We also need to measure the full system together. So we need to measure the distance to everything and map out a full coordinate system. Yeah, so let's see it flying. So here it's the lighthouse, flow, and LPS, and the lighthouse for the bend, and then the lighthouse for the landing. Very nice music. So that's it for me. But I would like to say something about other talks that is related to this. So today at 3 o'clock, Qualysys, Martin and Magnus will be talking about the Qualysys positioning system. At 4:30, Kimberly will be talking about advanced lighthouse usage, explaining in detail how the sweep works and how the system is set up. And on Thursday, Wolfgang will be talking about the Crazy Swarm. So that is it for me. Are there any questions about this? I am ahead of time.
Yes. Yeah, I think there were a couple of questions. I think Christopher's currently answering the one for the 2 Lighthouse base stations in the chat.
Yep.
Oh, sorry. You're able to hear me now?
Yeah.
Perfect. So there's also, I think, a question that perhaps you can answer. So, do we know the accuracy between TDOA 2 and 3 already?
No, I'm not sure if we've quantified this really. I'm not sure. What we kind of do know is that I don't know if there's a big difference. Two-way ranging is supposed to be better, but the difference between TDOA2 and 3, I'm unsure about. But they do have different properties. So like TDOA2 requires one anchor to be seen, the number 0, constantly. So this will affect how you can design and scale the system. Whereas TDOA3, the nodes are just ranging to whoever's in range.
Yeah. I guess it's also it's technically kind of like very similar, though in accuracy it's probably the same. It's just like in the properties of scalability. I think Christopher also had some comments on it. If he's not too busy with answering the 2 base station question, but
yes. I would say that TDOA2 and TDOA3 is pretty similar in accuracy, but TDOA3 is much more robust. So in my mind, TDOA3 is we learned stuff from TDOA2 and then we improved it into TDOA3. So I would personally not choose TDOA2. It is possible that it is slightly less noisy, but I don't think we haven't measured it, but I don't think we can see it either.
yes.
Yeah.
While you're here, I don't know how far you were with the chat and question of the achieving more than 2 base stations, but would you mind perhaps saying that out loud here, Christopher?
Yes, I can do that as well. So in the hybrid demo, I mean, in general, we do not have support for estimating positions of more than 2 base stations. And in the hybrid demo, I pretty much did it manually, merging the coordinate systems together. So right now there is no easy way. You have to be clever about it, sort of. Unfortunately.
But I guess like if you were to look on the blog post on our website about the hybrid demo, we have a link to our experimental Crazyflie firmware branch where we actually show the app layer where we implemented this, right? So yeah, I think for Osman that will be good to check that blog post out because it explains very clearly of how we try to achieve that. Okay, so Osman also had the question of, do you have a timeline of sharing the steps that you took? I think, yeah, I think looking at that branch, the hybrid demo branch from that blog post of, it's almost more than a year ago. It was a last Christmas video, right?
I think it was last fall, yeah.
Yeah, exactly. Yeah. So you have to kind of look back, but you can also use the search for it. And that kind of shows the timeline that we took, Osman. So please look for that. And then we also have Vital has a question. Is it allowed to port the software to another hardware than the Crazyflie firmware, like TDOA3 to create tags and anchors directly on the DWM hardware?
Yeah. I think the only limit is it's GPL free. So whatever you port it to, you are not allowed to lock. So you can't, with this license, you're not allowed to port it to a piece of hardware that you say to the users. You cannot update. You cannot
that's
update the
because of
firmware
that's the MIT's license that we use in our firmware, right?
GPL free.
GPL free, sorry, GPL free. Yeah, okay. So that kind of means it's like you're fine to use it, but if you're going to sell it commercially, you need to release the firmware.
Yes, yeah. As soon as you share whatever you put it on, you have to give access to the firmware, and you cannot lock. You must give the user the possibility to update the hardware and to change the firmware.
All right. Are there any other questions? Yes, Christopher has shared the link of the hyper demo in the chat. And Vital also has the question, are the licenses to pay for a commercial application?
Currently not, no.
No. I guess it's as long as it's like the firmware is readily available. I think that's the requirement. But I think that's perhaps like if you want to know a little bit more about that, then you probably should send us an email. Yeah. But yeah.